Welcome to the deep dive.
Yeah.
We hear these terms all the time: DDoS, SQL injection, phishing. They're constantly in the news.
They really are.
But just hearing the name, well, it isn't the same as understanding how they work, is it? If you really want to defend against these things, you need to know the mechanics behind them.
Absolutely. And that's really our mission today. We're taking the source material, digging deep, and trying to cut through some of that jargon.
Right.
We've sort of categorized these advanced threats based on, well, what they actually go after. Is it network capacity? Is it someone's identity? Or maybe, flaws deep inside an application's logic?
And for each attack, we're pulling out the specific defenses mentioned in the sources.
Exactly. What actually stops it? No fluff.
Okay, great. So where should we start? Maybe at the most brute force level. Attacks designed just to overwhelm systems.
Sounds like a good plan. Resource exhaustion. Everyone's heard of denial of service, DOS.
Yeah, DOS. But then there's DDoS, which seems much more common now. What's the key difference there?
Well, DOS, that's an attack coming from just one system. Pretty straightforward, really.
Okay.
But when you add that distributed, now you're talking multiple attacking machines, often thousands, part of a botnet.
A botnet, right.
And the result is the sustained, just crazy level of network traffic. The goal is simply to knock the service offline completely, make it unusable.
And some of these DDoS attacks get even nastier, right?
Yeah.
Using innocent bystanders. I'm thinking of reflected and amplified attacks.
Yeah, those really scale things up. They weaponize third-party systems. There's a subtle but really critical difference between them.
Okay, break it down for us. What's reflected DDoS?
Reflection is basically misdirection. The attacker sends a request to some legitimate third-party server, think DNS or NTP server.
Okay.
But, and here's the trick, they spoof the source IP address. They make it look like the request came from the target, the actual victim.
So the innocent server gets the request.
And dutifully sends its response back, but not to the attacker, no. It sends it straight to the victim whose IP address was on the request.
Wow, okay, so it's like sending someone else's junk mail using their return address.
That's a pretty good analogy, yeah. The attacker never sees the response traffic. The victim just gets flooded by replies they never asked for.
Got it. So what about amplification then? How does that differ?
Amplification adds, well, volume to the reflection. It means a small request sent by the attacker triggers a huge response from that third-party server.
Bigger response than the request.
Much bigger. Sometimes hundreds of times bigger. This is why certain protocols are abused so often, like DNS, NTP, SNMP. They're designed to provide a lot of information.
The sources highlighted NTP amplification as a kind of classic example. What's the specific vulnerability there?
It's actually fascinating. It involves older network time protocol servers. They had this diagnostic command called monlist.
Monlist?
Yeah. If you sent a monlist request, the server would respond with a list of the last 600 IP addresses that had connected to it. For diagnostics, you see.
600 IPs? That sounds like a lot of data.
It is, especially compared to the request. An attacker using a botnet just needs to send tiny UDP packets asking for the monlist. And again, they spoof the source IP to be the victim's address.
So a tiny request goes out.
And this massive response, potentially 200 times larger, listing all those IPs, gets blasted directly at the target. One small request from the bot turns into a huge flood aimed at the victim. That's amplification.
That's nasty. So if you're on the receiving end of this kind of flood, what are the key defenses? What do the sources say?
Well, there's no single magic bullet. It's all about layered defense. First up is rate limiting, basically capping how many requests your system will even bother answering from any one source.
Makes sense. Don't let one noisy source dominate.
Exactly. Then there's port blocking. If you don't need a service running on a particular port, just block traffic to it. Why leave the door open?
That practice anyway.
Definitely. We also use traffic signature filters. These look for specific patterns in the packets that are known to be part of these attacks.
Like looking for known malicious commands.
Sort of, yeah. And critically, you need threat intelligence services. These are feeds that provide lists of known malicious IP addresses, botnet CNCs, compromised servers. You can just block traffic from those sources preemptively.
Okay, that's a solid set of tools.
Yeah.
Before we move off resource exhaustion, quick word on the SYN flood. It's another classic.
Ah, the SYN flood. Deceptively simple, but it hits right at the core of how internet connections start the TCP three-way handshake.
Right. SYN ACK.
Exactly. The attacker sends the first packet, the SYN. The server responds with SYN ACK, and importantly, it sets aside resources like memory, expecting the connection to be completed. But the attacker never sends that final ACK packet. They just leave the server hanging, with resources allocated for a connection that will never complete. Do this thousands of times.
And you exhaust the server's ability to handle legitimate connections. It runs out of resources or it just crashes.
Precisely. That's resource exhaustion in a nutshell.
Okay, let's shift gears. From overwhelming resources to attacking identity. Impersonation, interception, what the sources call on-path attacks.
Right. This whole area often starts with forgery. Using something fake could be a fake security certificate, a fake user identity, even a fake file.
And spoofing is a major tool here.
Absolutely. Spoofing is all about making something look like it came from somewhere else. You've got IP spoofing, faking the source IP address, email spoofing, faking the sender's email address, very common in phishing.
And MAC spoofing too, lower level.
Yeah, faking the hardware address on a local network. The goal is always the same. Deceive the recipient into trusting the communication or granting access.
So that's making things look legitimate. What about actively getting in the middle of a connection? Man in the middle or MITM?
Now we're talking active interception. Positioning yourself right on the path between the user and the server, or between two servers.
And SSL stripping often comes up first here. How does that work? It sounds like it defeats encryption.
It kind of does, yeah. It exploits the initial handshake, the negotiation phase before the secure tunnel is established. The attacker sits in the middle. When the user's browser tries to connect via HTTPS,
The secure version.
right, the attacker intercepts that request. They then establish an HTTPS connection to the real server, so the server thinks everything is fine. But to the user's browser, the attacker forces the connection down to plain, unencrypted HTTP.
So the user thinks they might be secure or maybe doesn't notice the missing S, but the attacker sees everything in clear text.
Exactly. They can read, modify, inject things into the traffic because it's not encrypted between the user and the attacker.
Nasty. Okay, what about the classic network-level ITM ARP poisoning? That sounds technical.
It's a clever trick on local networks. ARP, the Address Resolution Protocol, is how devices figure out the MSE address, the hardware address, associated with an IP address. They broadcast a question. Who has this IP address?
Okay, standard network chatter.
Right. In ARP poisoning, the attacker floods the network with false ARP replies. They tell the victim machine, hey, the router's IP address, that's my MC address. And they tell the router, hey, the victim's IP address, that's my MAC address too.
Whoa, so they trick both ends into sending traffic to the attacker instead of directly to each other.
Precisely. The attacker becomes the invisible intermediary. All traffic between the victim and the router now flows through the attacker's machine.
And they can just sniff it all.
Yeah.
The sources had a graphic, right? Attacker at 192.168.1.66, sitting between the victim and the router.
Yep, that visual captures it perfectly. Complete visibility, complete control over that segment.
Okay, that's scary at the network level. But attackers are getting closer to the user, right? Operating inside the browser itself.
Yeah, the attacker and the browser techniques. Man in the browser is one. This is usually a Trojan horse, malware running on the user's machine.
A proxy Trojan?
Kind of, yeah. It hooks into the browser process itself and can modify web transactions as they happen right before they're displayed or sent.
What's the goal there? Stealing credentials.
Often, yeah. Eavesdropping, data theft, session tampering. These things often use keyloggers to capture everything you type, or form grabbing to steal data right out of web forms before you even hit submit.
Wow. And then there's browser in the browser. That sounds confusing.
It's super deceptive. It's a phishing technique, but a really sophisticated one. Instead of just faking a website, it actually simulates a complete browser window inside the user's real browser window.
Like a pop-up, but it looks exactly like a separate browser.
Exactly. It might look like a legitimate single sign-on prompt from Google or Microsoft, perfectly rendered, asking for your password, but it's all just HTML and CSS within the attacker's controlled page, designed to trick you into typing credentials into a fake window.
That's incredibly sneaky. Okay, let's pivot slightly. Away from direct interception, towards manipulating the systems that guide us online. DNS attacks.
Yes. Attacking the domain name system. If you can control where names point, you can cause widespread misdirection. Two main types here. First is farming. You can think of it as like phishing plus farming. It's usually localized. The attacker modifies the host's file on your specific computer.
The local lookup file.
Right. Or they might corrupt the DNS cache on your machine. Either way, when you type www.yourbank.com, your computer doesn't go to the real bank. It gets redirected to the attacker's malicious site.
So that affects just the one compromised machine.
Generally, yes. DNS poisoning, though, that's the bigger fish.
How so?
DNS poisoning targets the actual DNS servers, corrupting the data on the official servers that everyone else relies on. If you poison a server, potentially thousands of users could be redirected.
That sounds much more dangerous. How do we defend against that infrastructure-level attack?
The main defense here is DNSSE CNAS security extensions. It uses digital signatures to verify that the DNS data coming from the server is authentic and hasn't been tampered with.
So it adds a layer of trust to the DNS responses.
Exactly. And operationally, the sources also mention things like DNS filtering and sinkholing.
Right, sinkholes. How do those work?
Well, DNS filtering is pretty straightforward, using known block lists to stop connections to malicious domains. A DNS sinkhole takes it a step further. When a device on your network tries to connect to a known bad domain.
Like a command and control server for malware.
Exactly. Instead of blocking it, the sinkhole redirects that traffic to a controlled IP address, often a local non-routable one like 127.0.0.1, or maybe a server set up specifically to analyze this malicious traffic. It basically isolates the infected machine or stops the attack traffic from reaching its destination.
Okay, clever. Moving from domain names to actual user sessions, session hijacking. This is about stealing someone's active login, right?
Precisely. The attacker doesn't need your password anymore. They just need to steal your active session ID. This ID is usually stored in a browser cookie.
The thing that keeps you logged in.
Yep. If the attacker can steal that cookie, maybe through malware or an XSS attack we'll discuss later, they can present that session ID to the server, and the server says, "Oh yeah, I know you. You're already logged in. Come on in." They impersonate you completely.
Without needing the password. What about replay attacks? Sounds similar.
Similar concept, but often focused on credentials or authentication tokens. In a replay attack, or credential replay, the attacker captures some authentic data. Maybe your hash password being sent, maybe an authentication token, perhaps using a tool like Wireshark to sniff the network.
Okay, they record the valid data.
Then, they simply replay that captured data later, sending it again to the server to try and authenticate as you.
How do systems stop that if the data was valid once?
Timing is key. Good authentication protocols, like Kerberos, use things like timestamps and sequence numbers. This ensures that even if valid authentication data is captured, it can't be reused later because it's either too old or the sequence number is wrong. It makes the captured data stale, useless for a replay.
Makes sense. You know, the sources mentioned something crucial here, kind of an operational failure. Domain hijacking.
Ah, yes. It's important because while many attacks are super technical, domain hijacking often boils down to something simpler, like social engineering.
Yeah.
Tricking the legitimate domain owner into giving up their password for the domain registrar account, or maybe finding the password through other means.
Yeah.
Once the attacker has control of that account, they can change the domain's registration details, point the DNS records anywhere they want,
Right.
basically steal the entire domain identity.
The sobering reminder that sometimes the biggest vulnerability isn't the code, but, well, guarding the keys to the kingdom.
Exactly. Protecting those fundamental registration credentials is vital.
Okay, now for what I think is the really fascinating part. Attacks that exploit the application's own logic. Not the network, not the user identity, but the code itself.
Yeah, this is where things get intricate. And looking across the sources, the single most important defense that comes up again and again is input validation.
Input validation. Why is that so foundational?
Because almost every major application vulnerability, buffer overflows, SQL injection, command injection, cross-site scripting, they all start because the application trusts data that came from the user or from outside.
So you have to treat all input as potentially hostile.
Absolutely. Validation means checking a few things. First, the format. Is this supposed to be a social security number? Does it look like one? Is this a zip code? Does it have the right number of digits?
Okay, basic format.
And then boundary or range checking. If a field should only accept numbers between 1,000 and 3,000, don't let 999 or 5,000 through.
Right.
And crucially, blocking or sanitizing special characters. Things like angle brackets, which are used in HTML, dashes, apostrophes, equal signs. These can all be interpreted as code or commands by the backend system if you're not careful.
So input validation basically stops the attacker from sneaking code in through data fields.
That's the goal. And we need to be clear. There's client-side validation and server-side validation.
What's the difference?
Client-side happens in the user's browser, usually with JavaScript. It's fast, gives quick feedback, like telling you immediately if your email address format is wrong.
What?
But it's easily bypassed. An attacker can just disable JavaScript or use a web proxy tool like Burp Suite to intercept the request after it leaves the browser and change the data before it hits the server.
Ah, so client-side is convenient but not security.
Exactly. Server-side validation is the essential check. It happens on the web server after the data is received, right before it's processed or stored. It's your last line of defense, and honestly, it's usually pretty easy to implement. It must be done.
Okay, server-side validation is non-negotiable. Let's drill into SQL injection then. The sources had some really memorable examples.
SQL is a huge one. The goal is to get access to the backend database by tricking a web application that doesn't validate input properly.
How does the trick work?
Well, imagine a login form where the application takes the username you provide and plugs it into a SQL query, something like select from users, where username plus S.
Okay, standard query structure.
Now, what if instead of a normal username, the attacker enters this, or 1, or 11,
Or
right?
one, that's always true.
Exactly.
Yeah.
The query becomes select from users where username won't, or 11. Since 11 is always true, the where clause is always true for every user. At the end is usually a comment marker in SQL, telling the database to ignore anything after it.
So the database just returns all the users, or logs the attacker in as the first user.
It depends on the exact query and database, but yeah, it bypasses the intended logic completely. Another classic is breaking out of the query and adding a new one, like entering Daryl Gibson, select from customers.
So it finishes the first command for Daryl Gibson, then starts a whole new command to dump the customer's table.
Precisely. And again, the comments out the rest of the original legitimate query.
Wow. Okay, so input validation is the first step. But what's the best defense against SQL?
Input validation is crucial, yes, but the gold standard defense is using parameterized queries, often implemented as stored procedures.
Stored procedures. What are those?
They are precompiled SQL queries stored on the database server itself. The key thing is, when you use them, the input you provide, like a username, is always treated strictly as data. It's never accidentally mixed in with the executable SQL code.
So the database knows this part is the command, this part is just a value to look for.
Exactly. The structure of the query is fixed. You can't inject new commands into it. They can also handle validation logic themselves. It's much safer.
Parameterized queries and stored procedures.
Got it. Okay, let's talk about memory issues. Buffer vulnerabilities. These sound really low level and dangerous.
They can be catastrophic, yes. Three main types mentioned. First, a memory leak. This isn't usually an injection, but rather bad coding where an application keeps requesting memory but never releases it.
So it just consumes more and more RAM?
Yep, until it potentially crashes itself or even the whole operating system. Slow degradation.
Okay. Then integer overflow.
Integer overflow happens when you try to store a number that's too big for the variable type allocated to hold it, like trying to put the number 300 into an 8-bit integer variable that can only hold values up to 255.
What happens then? Does it just stop?
It often wraps around, potentially becoming a small or negative number, which can cause unexpected behavior or calculation errors. Sometimes it can be exploited, but buffer overflow is generally the more severe vulnerability here. Right, buffer overflow. This is the one we hear about leading to system compromise.
It is. This happens when an application receives more data than it allocated space for in a specific memory buffer. Think of pouring too much water into a glass.
It spills over.
Exactly. The extra data overflows the intended buffer and spills into adjacent memory areas. This adjacent memory might hold critical program data, function pointers, or return addresses.
And the attacker controls the data that spills over.
Yes. They craft the oversized input carefully. The goal is often to overwrite a return address on the stack, pointing it to malicious code, shellcode, that they've also included in the overflow data.
So they hijack the program's execution flow.
Precisely. The sources even mention attackers often padding their input with NOP instructions, no operation instructions, like the by 90 byte code. These act like a sled, increasing the chances that the hijacked execution pointer lands somewhere in their malicious payload, even if they don't hit the exact starting address.
That by 90 detail really shows the technical depth. Okay,
Yeah.
Related to injection, what about directory traversal and LDAP injection?
Directory traversal is about accessing files outside the intended directory. Attackers do this by manipulating file paths and input fields. They might use sequences like DOD to move up the directory tree.
So trying to access, say, system configuration files.
Yeah.
Like etc_pass on Linux.
Exactly. Putting etc_passvd into a parameter that expects a file name might trick a poorly secured web server into revealing that sensitive file. Mitigation is, again, input validation, and also running the web server process with minimal privileges so it can't access those files.
Makes sense? And LDAP injection.
Similar idea, but targeting LDD, the lightweight directory access protocol, often used for authentication or directory services like Active Directory. Attackers inject malicious LDAP query syntax to bypass access controls, escalate privileges, or just extract information they shouldn't see.
Okay, input validation seems key for both of those two. Finally, in this section, the cross-site attacks, XSS and XSRF. People often mix these up.
They do. Let's clarify. Cross-site scripting, XSS, is about injecting malicious scripts, usually JavaScript, into a website, which then gets executed by other users' browsers.
So the vulnerability is in the website, but the victim is the user visiting it.
Correct. There are two main flavors. Stored XSS, also called persistent XSS, is where the attacker's malicious script gets permanently saved on the web server. Think of a comment section on a blog. If they can inject a script tag into their comment.
Then anyone who views that blog post later has the script run in their browser.
Exactly. The script might steal their session cookies, redirect them, deface the page, whatever the attacker coded.
Nasty.
What's the other type? Reflected XSS or non-persistent. Here, the malicious script isn't stored on the server. Instead, the attacker tricks the user into clicking a specially crafted link, maybe in an email. That link contains the script in the URL parameters.
And the query string.
Right. The user clicks the link, sends the request, including the script, to the vulnerable website. If the website isn't careful, it might take that script from the URL and reflect it back as part of the HTML page it sends to the user's browser.
And the browser just runs it because it looks like it came from the legitimate website.
Precisely. It's reflected off the server back to the victim.
Okay, that's XSS injecting scripts into sites to attack users.
Right.
What about XSRF or CSRF, cross-site request forgery?
XSRF is different. It's about tricking a logged-in user's browser into making an unwanted request to a website they're already authenticated with.
How does that work?
Imagine you're logged into your online banking site. Your browser has the session cookie. Now you visit another website, maybe an attacker site, or even a legitimate site with a malicious ad. That page could contain hidden code like an image tag whose src attribute points to a URL on your banking site that performs an action, like transferring money.
MNG SRC http.mybank.com/transfer.to, attacker and amount 1000.
Something like that, yeah. Your browser sees the request to mybank.com, helpfully attaches your valid session cookie, and sends the request off. The bank sees a valid request from your logged-in session and processes the transfer. You might not even realize it happened.
Wow. So XSRF forces your browser to do something bad using your existing login.
Exactly. Thankfully, there's a strong defense. Anti-XSRF tokens. These are unique, unpredictable tokens embedded in web forms. The server checks that the token submitted with the request matches the one it expects for that session, preventing forged requests from other sites.
Okay, that's a critical defense.
Q.
That was quite a tour through the mechanics of these attacks. Let's shift to the final section. Defenses focused on secure coding and operations.
Right, building more resilient systems from the ground up. First, let's talk about race conditions. These are subtle timing flaws.
Timing flaws.
Yeah, it happens when you have two or more processes or threads trying to access and change the same shared data at roughly the same time, and the final result depends on who gets there first or in what precise order things happen.
Okay, like two people trying to update the same bank balance simultaneously.
That's a classic example. The sources mention a specific type called time of check to time of use, or toshti OU. This is where the program checks for a condition, like does this file exist, and then based on that check performs an action, like open the file.
Seems logical.
But what if, between the moment it checks and the moment it acts, an attacker manages to change the situation? Maybe they swap the file out for a malicious one. The program checked a safe file, but opens a dangerous one. That's a TOCTOU vulnerability, a state attack.
How do you prevent these?
Yeah.
Seems hard to control timing perfectly.
It is. For things like shared data access, mechanisms like database locks are used. They ensure that only one process can modify a piece of data at a time, preventing simultaneous conflicting updates. Proper synchronization is key in multi-threaded code.
Okay, now some of it sounds really interesting. Software diversity. What's that about?
It's a cool concept. The idea is to introduce randomness during the software compilation or build process. Even with the exact same source code, you compile it slightly differently each time, maybe changing memory layouts, register allocation, instruction sequences.
So you end up with many slightly different binary versions of the same program.
Exactly. The goal isn't to eliminate vulnerabilities, but to make exploiting them much harder and less reliable. An exploit crafted for one specific binary layout might crash or fail on a slightly different version.
So an attacker's carefully crafted buffer overflow might only work on a fraction of deployed instances.
That's the hope. It increases the attacker's workload significantly. It's about making exploitation less deterministic. We also need good error handling.
Right. Don't tell the attacker too much.
Exactly. Error messages shown to end users should be generic. An error occurred, please try again later. But the detailed error information, everything needed for debugging, should be logged securely on the server side, inaccessible to attackers. You don't want to leak internal paths, variable names, or database structures.
Makes sense. So how do we proactively find these bugs before attackers do? Code analysis methods.
Three main approaches mentioned. First, static code analysis. This uses automated tools to examine the source code without actually running it. It looks for known bad patterns, potential buffer overflows, unvalidated input, etc.
Like a spell checker for security bugs.
Kind of, yeah. Second is manual code review. This is where a human, ideally someone other than the original developer, reads through the code line by line, specifically looking for security flaws and logic errors. It's time-consuming, but can catch things tools miss.
Need that human expertise.
Definitely. And third is dynamic code analysis. This involves actually running the code and testing its behavior. This includes techniques like fuzzing.
Fuzzing. Sounds fun.
It means throwing lots and lots of unexpected, malformed, random data at the application's inputs to see if you can make it crash or behave strangely. Crashes often indicate potential vulnerabilities like buffer overflows. Dynamic analysis also includes running the code in a sandbox and isolated control environment to observe its behavior safely.
Okay. Static, manual, dynamic. A combined approach seems best.
Absolutely. Finally, for web applications, there's a lot of protection you can get just by setting the right HTTP headers. OSB has great guidance here. Well, HTTP Strict Transport Security, HSTS. This header tells the user's browser, hey, for the next year, only connect to this site using HTTPS. Don't even try HTTP. It prevents those SSL stripping attacks we talked about.
Powerful.
Then there's Content Security Policy, or CSP. This lets the server define exactly where the browser is allowed to load resources from scripts, images, CSS, fonts. If an attacker manages to inject a script tag trying to load malware from evil.com, CSP can block it because evil.com isn't on the allowed list.
Nice. Controls the content sources.
And X-frame options, which helps prevent clickjacking attacks by controlling whether your site can be embedded within an iframe on another site. All these headers add significant layers of defense, managed right at the web server level.
And tying a lot of this operational security together is scripting and automation.
Yeah, scripting is huge for efficiency, consistency, and security. You can automate security checks, enforce configuration baselines, deploy patches reliably, scale security measures across many systems, and integrate security testing right into the development pipeline. Continuous integration, continuous testing. It reduces human error and ensures security is baked in.
Wow. What an incredible deep dive, truly. We've gone from brute force DDoS right down into the weeds of memory corruption, SQL injection logic, and secure coding practices. It really covers a massive range of threats.
It really does. And I think the main takeaway is that there's no single fix. Protection is always layered. You need strong technical controls, things like DNS ACC, parameterized queries, solid input validation. But you also need secure operational processes guarding those domain credentials, using automation, doing the code reviews. It all works together.
That's a perfect summary. It really highlights the complexity. So, thinking about everything we've covered, from the highly technical race conditions exploiting tiny timing windows to something as fundamental as domain hijacking, often succeeding through basic social engineering, what really stands out is the weakest link. Is it the complex tech flaw, or is it sometimes just that simple human element of guarding the basics?
That's the million-dollar question, isn't it? Something for you, the listener, to really think about as you work to secure your own part of the digital world.